We'll start with model assembly. So first we'll import the BOM file. The BOM file may or may not come from your PDM system or contain PDM information. If it does, that does automate some level of organization. So first, let's load the 5mm representation for the part sets associated with our load paths. The next thing we'll do is we'll load a coarser 10mm representation for the rest of the vehicle. Now we're going to skip loaded here because we already have a 5mm mesh representation loaded for those associated with our load path set. So now we have a 150% BOM of our body in white. So let's say we want to take a look at the shock tower and replace it with a casting. So let's walk through how we might create a mesh manually using our new direct mid-meshing tools. So the first step is to generate the initial mid-mesh. So we'll submit the geometry to mid-meshing to generate that starting point. From here, these tools operate on the mesh representation of the midplane, not a geometric one. So editing faces, filling in faces, or removing features from geometry onto the underlying mesh will now dictate how the batch mesher handles them when we perform a rebuild in the end. So we're able to create new edges by nodes or derive them from the geometry. We are able to imprint features from lines from the solid to get additional detail, or we can suppress features, feature lines where the detail is no longer required. We're able to align edges and faces according to the geometric topology as needed. For example, when the automatic process fails to represent a perfect circle here. And from the clean topology mesh representation, the last step will be using the mesh rebuild process, which will use the batch mesh criteria, in this case 5mm, to remesh the part, submitting the topology result as input. Finally, mapping the thickness is a feature that has been in HyperMesh for quite some time, but is mostly ignored. Now, in our new user interface, it is discoverable and at the end of the ribbon as the last step in the workflow. Now that we have this new part mesh, we'll bring it back into the body in white. So let's now organize our BOM using the attributes provided to us from the CAD system. From here, we can see that we have flags for a fixed roof, panel roof, left-hand drive, and right-hand drive. The part sets for these have been automatically created from the PDM flags. The only step left is to drag and drop these part sets into 4 different vehicle configurations. So here we drag the left-hand dash, the panel roof, for one configuration, and then repeat the same process for the other 3 configurations. So when we are done, we'll be able to toggle on and off each of the modular assembly representations. It should be noted that if you do not specifically select part representations to belong to a configuration, they belong to the common model, so they will be associated with all vehicle configurations. So this is only necessary for those that belong to a unique configuration. So here we are toggling the active vehicle configuration between the 4 configurations: left-hand drive, right-hand drive, fixed, roof. So the next step in our process is to realize connections, which also may have different representations. So here we're going to load connections from our connector library. And here are the connectors for the body in white. We can realize connections right from the idle state. In this case, we'll realize spot welds and adhesives. Here you can review the type of connections that have been realized. Note that we create parts for all of the connectors so that they can be easily assigned to a part and then moved to a subsystem. So finally, we create a subsystem for our body in white and save the subsystem to the subsystem library. And again, when we save these into the subsystem library, that also facilitates a collaboration with other teams that may be sharing the same library. So the next step would be move to the Subsystem Browser. So our subsystem workflow is analogous to our part browser workflow. So we will ensure we keep track of all the entities that belong to the existing subsystem, but also we want to maintain the subsystems from existing include files. So we'll load the remaining include files from an existing HyperMesh binary. We allow dragging and dropping of any entity from any view in the model browser, in this case into the Subsystem Browser. So we have includes created, or excuse me, we have subsystems created from each of the individual includes, and then we can make sure that we save these all as a subsystem representation for our crash model. We also support subsystem color mode now, which enables an easy visualization of all the entities within each subsystem. We also allow multiple representations of subsystems, either from the same solver or any number of our supported solvers. So the next step is to generate separate load case configurations with the Subsystem Browser. From here, you can now associate each one of these includes to its own subsystem configuration via subsystem sets, which are analogous to the part browser's part sets. So we've organized all of our includes associated with an offset barrier left-hand side, a right-hand side, and a side impact. So here the subsystem sets contain only those includes that represent each of these load cases. And any subsystem that is not explicitly called out with a subsystem set, analogous to the part browser, is associated to a common subsystem, which means it belongs to all of the load cases. So for any active load case configuration now, we can now export a complete set of input decks for any one of these load steps, running out each of the subsystems, simply by activating its load case. Now that we've defined our load case configurations, a key feature to leveraging the subsystem representations are the subsystem attachments, which is new for 2020, supporting bolted connection types. Here we'll realize bolted joints between our body and white and the door subsystem. We can realize these bolts many different ways. Here we choose a configuration of the attachments to be rigid patches. Our rigid patch realizations for bolts support OptiStruct, Radios, and Dyna. Our new attachment controls are also solver agnostic, so this removes one of the largest bottlenecks in the model assembly process. Our holes can be selected or auto-detected. In this case, fill hole is used, and the rigid patches are automatically generated between the two subsystems. Also note that when the rigid patches are realized, they're automatically organized into their appropriate subsystem, which is made clear by our new subsystem color mode. Next, we would like to generate a new subsystem to place these attachments so they can be added to our vehicle configuration and then realized and unrealized as we change our vehicle configurations. Here we're reviewing the rigid patches with the same visualization tools we use for contact pairs on the rigid body merge part. Finally, we'll realize the rest of the connectors for the other subsystems that we loaded into the model. Everything outside of the body and white has been realized now, and the user can export a set of solver decks for any one of these vehicle configurations in all of our defined load step configurations.